Welcome to Tortoise Water discussions. It's just going to be me on my own today. I'm going to be clearing up a few things from our first galaxies video and then exploring the idea of the expansion of the universe. Turns out I was completely wrong about first galaxies, or in first galaxies, about how big the universe actually is. I thought because light has only traveled 14 billion light years, that the universe radius would be 14 billion light years. It turns out it's actually 46 billion light years across, and that's caused by the expansion of the universe, but I'll get to that in a bit. In that first galaxies video, the galaxy that we see at the edge of our sphere that is close to the Big Bang is actually 46 billion light years away from us, not the 14 billion that I stated. But all that really does for the perspective is it makes the universe so much larger, because now it's not 14 billion light years across, it's 46 billion light years across. And as we talked about in the first galaxies video, dark energy and dark matter make up most of that. All the galaxies we see, all the stars we see, make up 1% of the total mass of the universe in a 46 billion light year radius. That is huge. That 1% ties in nicely with something I read recently, that the European Space Agency is sending up a satellite called Gaia that's going to map 1 billion astronomical objects in our galaxy, and that's only considered to be 1% of our galaxy. So there's 100 billion astronomical objects just within our galaxy alone, and we are one galaxy within clusters of galaxies spread throughout a 46 billion light year radius. Now, getting on to the expansion and why it is actually, the universe is actually bigger than the 14 billion years of its age. It turns out that the expansion of the universe, which has been accelerating since the Big Bang, has allowed portions of the universe to expand away from each other faster than the speed of light. If you take two sufficiently far enough apart galaxies, those galaxies are likely to be expanding away from each other faster than the speed of light. Now, my basic understanding of this expansion is, first off, I don't think it happens within galaxies itself, or maybe even between galaxies in their cluster, but it would happen in the massive expanses of space between clusters of galaxies. So if two galaxies are in two very far apart away clusters, then they would expand apart from each other faster than the speed of light, because there is space in between them, or more space in between them, that is expanding at the same time to allow them to go faster than other objects that are closer than each other. So hypothetically, if you could divide the distance between these two separate objects and put it into square centimeters or square meters or whatever it is, the more portions of space that exist between those two objects, the more space will expand, and therefore the observer would, on one galaxy, would see the other galaxy going faster than the speed of light. Now, I said the observer there. The observer in this case is a crucial aspect in determining if something is going faster than the speed of light. And we as observers have seen galaxies that are actually redshifted enough for us to believe that they're escaping away from us faster than the speed of light. Interestingly enough, though, that even though they are now traveling faster than the speed of light, it'll still take a few million years to actually reach a point where their light will no longer reach us, as they will be expanding fast enough away from us that the light will never actually be able to catch up. Whereas in this one or a couple million year time frame, that light will not reach us at the speed of light, as far as I understand, but will eventually catch up to allow us to receive that light. This got me thinking of our own local stellar neighborhood and how hard it would actually be for us to just travel a few light years away. And it turns out it would be very, very hard. The closest star to us is Proxima Centauri at 4.24 light years away. That's 9.3 trillion kilometers. And if we went at a constant speed with enough fuel and food and everything like that, in a spacecraft that went as fast as the fastest man-made object we've ever created, it would take us 4,000 years to get there. The fastest man-made object was the Helios 2 spacecraft, which circled the Sun, and because of its gravitational pull was able to reach speeds of 248,000 kilometers per hour. You could go around the world. That's what the world is, 40,000 kilometers across. You could probably go around the world about 5-6 times every hour. At the equator, anyway. But the Helios 2 spacecraft actually totally decimates the fastest human that has ever gone, or the fastest a human has ever gone, which was only about 40,000 kilometers per hour. And that was the Apollo 8 mission. So now looking back on all that, you've got a universe that's 46 billion light years across. You've got our own galaxy, which has 100 billion astronomical objects, which I assume to be stars. And then you've got the human race living on a tiny little planet that would take 4,000 years just to get to our closest stellar neighbor. Our only opportunity to make any sort of headway in the universe and to explore it efficiently and effectively obviously leads me to believe that we would need to find ways to go faster than the speed of light. Or alternatively, we don't even go fast. We just invent some sort of teleportation or wormhole, or we figure out something. At least that's what I hope anyway. Otherwise, we're pretty much going to be stuck in our little old solar system for a very long time. Thanks for listening to my ramblings. If you liked it, give it a like. If I said something stupid, put down a comment. If I said something smart, put down a comment. If you want to see more new videos, just subscribe. And if you want to send us a message, we're also on Twitter at Tortoise Water.